Hey folks, welcome back to the EDM Studio. Today I'm going to be talking about signals in the complex plane, which is essentially a way to capture the phase of a signal, which is something that I've glossed over in the past. And the reason that I want to talk about this subject is that I'd like to do a video on the ES-FM1 synth, which is the built-in FM synthesizer in Logic. But to really understand what is going on there, you need to have at least a basic intuitive understanding of sidebands. And that's kind of the most interesting thing about FM synthesis. So today I'm going to talk a little bit about how those come about and some other ways of thinking about those frequency plots that we talked about in the signals video. So let's begin with this picture up here. Now, in the past, when we talked about frequency domain, we talked about just energy at certain frequencies. So we'd say like, oh, this signal has a peak of energy at 200 hertz. But what I was really glossing over when I talked about that was that there's this other component of that picture, which is phase. And a good way to illustrate that is you think about a sine wave and a cosine wave. Now these are trigonomic functions. And basically what they're capturing is the phase of the same signal. So this is a cosine wave. It starts at 1, and then it descends to -1, and then back to 1. A sine wave, on the other hand, starts at 0, goes up to 1, down to -1, and then ends at 0. So these are the same basic waveform, but they are shifted in phase. And if we only thought about amplitude in those plots that we talked about in the signals video, these two would appear to be exactly the same. That works for some effects, but when you're talking about FM synthesis, or actually modulation in general, the phase really matters. So we need some way to capture that information as well. And the way that we do that is we think about signals in terms of the complex plane. Alright, had to move my board a bit to fit all the math in the picture. So what do we mean when we're talking about a complex plane? Well, most numbers you're familiar with are what we call real numbers. They're just regular old numbers that you use in math. They also can have what we call an imaginary component, and that is a component that relates to the square root of -1. So we call that j. This up here is a famous theorem called Euler's theorem, I believe, or Euler's relation, and what it's saying is that a exponential that uses this complex notation is equal to the cosine and sine components, separated with cosine representing the real component and sine representing the imaginary component. So for the purposes of these audio signals that we're trying to analyze, you can think of it as cosine is captured by the real component, and then the sine component is captured by the imaginary component. One way to visualize that is in terms of what we call a Phasor diagram. So in this diagram we have the real axis, or the x-axis representing the real component, and the y-axis representing the imaginary component. And our phasor is this thing that moves around in a circle. And it's representing the periodic signal over time. And one way that you can kind of see that this is the case is, let's say that we want to look at just the cosine component. So that's the real axis component. Now if we start at 0 degrees, that means that the real component will be equal to the length of this phasor, which is 1. So we have 1 at 0 degrees. Now let's say we rotate 90 degrees, or in many cases when we talk about signals like this, we actually use what we call radians. And that's just to make the math a little bit easier, but pi radians is equal to 180 degrees. So we rotate 90 degrees, and now we have x-axis value of 0. Rotate another 90 degrees, we have an x-axis value of -1. Another 90 degrees, we're back to 0. Then another 90 degrees, and we're back to 1. You can see in this plot, over 2 pi radians, we go, cosine. We start at 1, 0, -1, 0, 1, 0, negative 1, 0, and so on, just like as we rotated around here. Similarly, you can visualize a sine plot by looking at the y-axis. So sine starts at 0, goes to 1, goes back to 0, goes to negative 1, and so on. Just like the time domain plot here, 0, 1, negative 1, 0, right? So that is where the real and imaginary components come from. And what they're really mapping to is what component of our audio signal is represented by a cosine wave in phase, what component of our audio signal is represented by a sine wave in phase. And between those two, we can capture all of the phase information about the signal. Now, mathematically, this is one of the most difficult concepts to understand in signals. It took me a whole quarter while in class in this to really grasp it, but it's incredibly powerful. And this is called a Fourier Transform. I'm going to try and explain just conceptually what this is capturing. And I'll also link to a couple docs that I thought were helpful. But this is really at the heart of what those frequency plots we looked at in the signals video are saying, except it's also capturing phase information. This is saying the Fourier transform of our time domain signal, that's the audio signal that you're going to broadcast out of your speaker, we're going to call that big G of t. Big G of t is equal to the integral over little g of t times this complex exponent that is representing cosine and sine components of the signal. So basically we're looking over your whole signal to figure out what are the frequency components in terms of sine and cosine, and how much are they represented in your final signal. Now, here is really the heart of why I wanted to do this video, and this is where the Fourier transform comes in when you're talking about modulation. Particularly modulation with these simple signals like a cosine or a sine wave. Remember, last video I talked about a low frequency oscillator. That is a form of modulation. So all this crazy math just appeared, and what I wanted to do was show that cosine and sine are these special cases that can actually pretty easily be shown to be written in a form that comes out of this Fourier transform. So a cosine has energy with an amplitude of 1/2 at positive W and at negative W. So the positive frequency and the negative frequency. Remember, now we can talk about frequency in terms of that phasor spinning around the real imaginary plane. And it makes sense that maybe that phasor could also spin the other direction, right? So now we've given a visual representation to what a positive frequency is and a negative frequency. Sine actually can be written in a similar way, except it's purely imaginary. So it has an amplitude of 1/2 in the imaginary plot at a positive frequency of W, and then a negative amplitude at a negative frequency of W. So here's sine, and here's cosine, and here's sine. And just to show that, I didn't make this up, we have this giant block of math, but it's actually really not that complex. So let's just look at this relation I mentioned with the half amplitude at the positive W and half amplitude at the negative W. Now using that Euler's relation, you can substitute in the relations. So now we have 1/2 Euler's relation plus 1/2. And this also comes from Euler's relation, but notice we have the negative j here because we had the negative j in the exponent. So then you can expand the 1/2 to each of these, so you get 1/2 cosine plus 1/2 j sine plus 1/2 cosine minus 1/2 j sine, and then the imaginary components cancel out. And we get 1/2 cosine plus 1/2 cosine, which is equal to cosine. So all of that really is meant to just get you to this picture, because this is what's important for what I'm going to talk about next. And the key is to see that we have this positive frequency component and then the negative frequency component. And those are going to create what we call sidebands. And that's really the most interesting part of modulation, because we can do all sorts of really cool stuff with that to broaden the frequency spectrum of your instrument. So I'm going to do another video on that. I hope this made at least some intuitive sense, and again I'll link to some other stuff, but really this is what we're going for. You get these sidebands. So that's that. I'll see you in the next video. Thanks.